In this module, we're going to be talking about kinematics, which is the study of motion, and specifically, we'll be dealing with motion in one dimension. Next module, we'll talk about motion in two directions. Now, this particular video, we'll be dealing with horizontal motion, and the first definition you need to know is that of displacement. Displacement is defined as the change in position of an object, and mathematically, it's delta x is equal to final position minus the initial position. So we use delta x because we're talking about the x-axis here, horizontal motion. Now, physics makes a distinction between distance and displacement. Displacement, as we just said, is the change in position of the object, whereas distance is the length of the path. So, for example, if you're on a quarter-mile track and you circle the track once, then your distance that you traveled is a quarter mile, but the displacement would be 0 because the final position and the initial position are the same. Now, in some instances, when they're going in the same direction, then distance and displacement will be equal, but certainly not always. Okay, now another important point is that of a vector and a scalar. Now, we'll be discussing vectors more in the next module, but a vector is any kind of quantity that has both magnitude and direction. Scalars, on the other hand, only have magnitude and no direction. So, for example, displacement here is a vector quantity. It always has a direction associated with it, whereas distance is a scalar. More about that later. Okay, now the next thing is velocity. Now, velocity is defined as the rate of change of displacement. So, anytime in physics you'll see rate, that almost always implies time. So the actual formula for computing average velocity is change in displacement over time. Notice that little bar over the V there, that indicates that this is average velocity. Units are typically meters divided by seconds, although those units of displacement could be centimeters, kilometers, or whatever, but it's units of displacement divided by time. Now, skipping down here for a minute, speed, on the other hand, is defined as distance divided by time. So there is a distinction between velocity and speed. Speed, by the way, is another example of a scalar, whereas velocity is a vector. Now, you should also note that there's a difference between instantaneous velocity and average velocity. As the name implies here, instantaneous velocity is the velocity in a particular instant. So, for example, if you're traveling down the Northway and you get stopped by a state trooper for doing 80 and a 70, that 80 miles per hour is your instantaneous velocity. On the other hand, your average velocity from, for example, when you left home is probably a lot different. So next time you get stopped by a state trooper, you might try to say, yes, officer, my instantaneous velocity was 80 miles per hour, but my average velocity was only 50. And see how that works out for you. Now, you'll often have to solve that previous equation for displacement. So that's a very easy algebraic manipulation. The displacement is simply equal to the average velocity times time. So, for example, you might have an average velocity of 20 meters per second, and the displacement covered over 2 seconds would be 40 meters. All right, now, the acceleration is the rate of change of velocity. Now, it's important that you don't get acceleration confused with velocity. Acceleration is the rate of change of velocity. Notice that the change in velocity is equal to the final minus initial. also know that velocity to the right is considered positive and to the left negative. And that needs to be included when you're computing this delta V. Is the final velocity positive or negative? Is the initial velocity positive or negative? Okay, then the average acceleration, therefore, is equal to the change in velocity divided by time. The units of acceleration are meters per second squared, and the reason, or the way that we get that, is that the units for the change in velocity are meters per second, and we're dividing that by units of time, which is seconds. So if you work this out, just algebraically, meters per second divided by seconds, you will come out with meters per second squared. Okay, so here's a very simple example. If you have an object starting from rest and accelerates uniformly at a rate of 2 meters per second squared, remember we're thinking about that as meters per second, what will be its velocity after 5 seconds? So, after 1 second, the object starts from rest, its velocity is 2 meters per second because the velocity is changing at a rate of 2 meters per second every second. After another second, its velocity is now 4 meters per second. After 3 seconds, 6 meters per second. After 4 seconds, 8 meters per second. And after 5 seconds, 10 meters per second. So notice you actually just multiplied the acceleration times the time to get that final velocity, assuming that the object did start from rest. Now, I said in the last slide that the velocity of an object to the right is positive and to the left is negative. Now, it's certainly possible that velocity and acceleration can have different directions. So, if the velocity and the acceleration are in the same direction, then the object's velocity is going to be increasing either in the positive or negative direction. So it's either going to be going faster to the right or faster to the left if the velocity and the acceleration are in the same direction. If they're in the opposite direction, then the velocity is going to be decreasing, decelerating. So if the velocity is to the right, the acceleration is to the left, then the object is going to be slowing down as it moves to the right. Or, on the other hand, if the velocity is negative, moving to the left, and the acceleration is positive to the right, then the object is going to be slowing down or decelerating as it moves to the left. Now, there are 4 basic equations for uniformly accelerated motion. So when I say uniformly accelerated motion, I mean when the acceleration is constant. These 4 equations right here are going to be used in problems that you'll have to solve. My advice to you is to maybe get out an index card, write the 4 equations down so that you can refer to them as you're solving problems. Okay, let's just run through them quickly. So, first one is when you need to calculate the final velocity for an object accelerated for a known time. So here's your final velocity. It's equal to the initial velocity times the product of the acceleration times the time. Actually, this is the formula that we used in that previous little problem that we did in the previous slide, where we just basically took the acceleration and multiplied it by the time to get the average velocity. The initial velocity, if it starts from rest, is going to be 0. Okay, now the next one is for calculating the displacement of an object for a known time. So here's the equation. X is the displacement. It's equal to the initial velocity times the time plus 1/2 times the acceleration times the time squared. The next one is for computing the final velocity for an object accelerated for a known displacement, delta x. So that's equal to the square root of the initial velocity squared plus 2 times the acceleration times the change in displacement. And then the last one is for the average velocity during uniform acceleration. And this is just equal to the initial plus the final divided by 2. And this one should be intuitively obvious if you think about it. An object is accelerating uniformly, and the average velocity is going to be between the initial and the final. So you would just take the initial plus the final and divide by 2 to get the average. Okay, once again, these 4 equations are very important. They are derived in the text, and you should take a look at that derivation and follow them through so that you can understand where they came from. And they'll be used in many of the problems that we work on, not only in this chapter, but in subsequent chapters. So let's try a couple of problems using those 4 equations. So here's one. We want to find the displacement for an object starting from rest and accelerating uniformly at 5 meters per second squared for 2 seconds. Now the first thing you have to do is find the equation that includes what you are solving for, in this case the displacement, and the quantities that you're given, the acceleration and the time. So if you look at those 4, you'll probably come up with this one right here. X is equal to initial velocity times time plus 1/2 at squared. Now, the object starts from rest, so this is going to simplify matters a little bit because the initial velocity is 0, so this whole term is 0, so it just reduces down to x is equal to 1/2 at squared. Substituting the values in, x is equal to 1/2, the acceleration, 5 meters per second squared, the time, 2 seconds, okay? Now, you want to calculate the answer, so it's going to be 2 squared is 4, times 5 is 20, times 1/2 is 10. Okay, I'm writing it as 1.0 times 10 to the 1 meters, because I need to keep 2 significant figures in the answer, because right here, this is the smallest number of significant figures, which is 2. So that's how we need to write that. Also, notice, very important, that when you square 2 seconds, you're going to get 4 seconds squared. And then the second squared and the second squared in the denominator here of the acceleration is going to cancel. So you'll be left with units of meters. All right, let's try one more problem. This one states how long of an airstrip would be required for a plane that must reach a speed of 27.8 meters per second for takeoff, assuming it can accelerate at 2 meters per second squared. Now, in this case, we are looking for a displacement, how long of an airstrip, and we know the final velocity that's required and the acceleration. So this particular equation is going to work for us, but we're going to have to solve algebraically for that delta x. Okay, so again, initial velocity is 0, so this term drops out here. And if you solve for delta x, you'll find that delta x is equal to v squared minus v0 squared over 2a. Okay, again, this one is 0. So it's 27.8, okay, meters per second, and that's going to be squared, divided by 4 meters per second squared, or 193 meters. And if you work through those units, again, you will find that units indeed do come out to be meters, since you've got meters squared over seconds squared in the velocity, and then you're dividing that by meters per second squared. Again, we keep 3 significant figures in the answer because both of these quantities here have 3 significant figures.